Hello, in this video I'm going to talk about moles. So not the furry little creatures, but the measurement of an amount of substance. And this is particularly useful in thermodynamics, as it is in things like chemistry, because we're talking about the macroscopic and the microscopic at the same time here. We're taking macroscopic properties. In this case, we're particularly interested in mass, so an amount of matter, but we're acknowledging the fact and analysing it partly in terms of the fact that it's made up of huge numbers of particles at the microscopic level. So we want some way of being able to talk the language of the macroscopic and the microscopic at the same time. And moles certainly makes this easier. Now, historically speaking, 1 mole of a substance is equal to the number of atoms in 12 grams of carbon 12. So that was what they initially decided was going to be the definition of what a mole is. So we can say 1 mole, or the number of atoms in 12 grams of carbon 12, is Avogadro's constant. So that's something that you probably would have come across because it comes up all over the place in science, and that is around about 6.02 times 10 to the 23 atoms. So if we've got some other substance made up of whatever it is, atoms, molecules, if we've got 6.02 times 10 to the 23 of those atoms or molecules, that means we've got 1 mole of that substance. So we've got a nice link here between a good macroscopic quantity here. We're talking in the world of grams. Okay, a little on the small end, maybe. It's not kilograms or something, but we still got grams. This is a manageable everyday macroscopic quantity of matter that we're looking at, where we've got grams as our mass measure. So we've got macroscopic here. But then we've got the nice view here on the microscopic level of saying, well, we've got an enormous number of microscopic particles or entities. So we've got that link now between those two things. Now, we can then, so of course, if we've got n moles of a substance, so n moles of a substance will have a number of particles, n, which is equal to the number of moles multiplied by Avogadro's constant. So n moles of a substance, this is all we're doing every time. If we want to work out the number of particles that we've got, we take the number of moles and multiply by Avogadro's constant. That gives us the number of particles. So that is the number of our particles, whether it's atoms or molecules or whatever. And if we want to work out the number of moles, we take the number of particles and we divide it by Avogadro's constant. So we got an easy way of flicking backwards and forwards here between the macroscopic and the microscopic. Now this allows for quick calculation, but as we've seen in our structure of matter studies, it also introduces approximations. Because if, say, we were going to compare molar mass of things, so molar mass is our mass of 1 mole of a substance. So we've seen this already here with carbon. Our molar mass of carbon 12 is 12 grams. That's what we've defined the mole off of, at least historically speaking. We've got this definition up here. So let's say we were going to look at carbon dioxide then, and we say, okay, well, if we've got our 12 nucleons in carbon 12, so we've got our 6 protons and our 6 neutrons, so we've got 12 nucleons there, and we say, okay, well, in CO2 we've got 12 in the carbon, we've got 16 in the oxygen, and there's 2 lots of oxygen, so we've now got 48 nucleons versus 12 nucleons for the carbon 12. So we've got 48 grams in 1 mole of carbon dioxide versus 12 grams in 1 mole of carbon 12. So this is our molar mass off of a very quick calculation for CO2. That's our molar mass of CO2. This is our molar mass of carbon 12. The thing is, we've seen with binding energy that you don't get exactly the same. Not all nucleons are the same. You know, we bind together nucleons in our CO2, and they're going to have a different binding energy than the nucleons in our carbon-12. So there is going to be a difference in the mass, because the mass of these atoms and molecules depends upon the binding energy. You know, we've seen we get mass defect in these sort of things because we've got a difference in the mass energy that's inside these particular atoms and molecules in the way that they're bound together. So we are getting approximations thrown in, and when you start out in all of this sort of stuff, and even later on, I mean, it's a bit like when we're doing with classical mechanics. It's close enough. Okay, it's good enough for basic purposes. There are going to be some situations where we want to measure these things more accurately, but when you're starting out, it's okay just to do these simple calculations of molar mass. So, but this has now been tackled, in 2019. I'm always going on about these revisions made to the SI units. And in 2019, again, they made changes to this. So rather than saying the definition of a mole was the number of atoms in 12 grams of carbon-12, it's now been changed around in the way that they did with most things. And so, well, let's fix the constant, because we can fix that. And then we'll take all of our definitions off of that. So they redefined Avogadro's constant, and they said, well, Avogadro's constant is exactly 6.02214076 times 10 to the 23. We will make that exactly what Avogadro's constant is, and then we'll define everything off of the back of that. So the mole comes off of that definition. So we've seen that trend going through those 2019 redefinitions of base units. Of course, this still allows people to celebrate Mole Day. There is a Mole Day has been coined, where and this runs from 6:02 in the morning to 6:02 in the evening, coming off of the first three digits that we've got here on the 23rd of October, coming off of our 10 to the power of 23 there. So that is our Mole Day that you get some nerdy chemists decide they're going to celebrate each year, or at least acknowledge. So when it comes to measuring Avogadro's constant, which is obviously the key point now to, okay, it's been fixed here, but how did this number come from? And this is the key determinant for what a mole is. How has that number been decided upon? Now, I mean, it's named after Avogadro because in the first part, the early 19th century, it was Avogadro who proposed that for an ideal gas, the volume is proportional to the number of particles. So whether that's in moles or whether that's just the capital N for number of particles, if you've got a fixed temperature and pressure. So we fix those, and then we can see that the volume of the gas is determined by the number of particles, or vice versa. There's a proportionality between them. And it was these ideal gas measurements and experiments that gave the first estimates for what Avogadro constant actually is, what the value is. Now, there was a breakthrough in the early 20th century then for determining a more precise value for Avogadro's constant. And that came because of the Millikan experiment, the one where you're determining the charge on the electron, where you've got the oil drop, and you're getting that oil drop in equilibrium where you're balancing an electromagnetic force with a gravitational force, and you're using that to work out the charge on the electron. Now, it might seem weird that that was then a breakthrough for working out a better value for Avogadro's constant, but that's because in 70 or 80 years prior to the Millikan experiment, Michael Faraday had been doing work on electrolysis and come up with the Faraday constant. And the Faraday constant had been determined, fairly accurately. And it was known that that was the charge on the electron multiplied by Avogadro's constant. So if we knew one of these ones on the right-hand side, because we knew Faraday's constant, we could then work out the other. So knowing Faraday's constant and the charge on the electron then gave a good estimate, or a better estimate, for Avogadro's constant. So the charge comes into this because electrolysis, which is what Faraday was working on, if you're not familiar with it, that's where you're driving chemical reactions by passing an electric current through the reactants. So these reactions don't just occur spontaneously, but if you stick a bit of energy in, then you can get these reactions to happen. So he was looking at rates of reaction, and that was what was allowing him to determine this Faraday constant, and he knew it had something to do with the number of electrons that were involved in the reaction. So yeah, that gave a really big breakthrough then in getting this better value. And of course, this was getting refined until now, 5 years ago, whether it was in 2019, they've decided to fix Avogadro's constant at that particular value, which has now fixed our definition of what a mole is. But the main thrust behind all of this, as I said at the beginning, is the fact that moles are allowing us to flip between the microscopic and the macroscopic, something that we're going to see in our two ways of writing out the ideal gas equation, where you've got a PV equals nRT with a lowercase n, where we're describing things here all macroscopically. We've got our pressure and our volume, we've got our number of moles, we've got our temperature, and then we've got a molar gas constant. And we've got a sticking a toe into the microscopic equivalent of this, where we've still got the PV and the T, but then we're looking at the total number of particles and the Boltzmann constant. So we've got a capital N KT on the right hand side. So these are two different ways of writing out our ideal gas equation, one in terms of macroscopic and moles, another in terms of microscopic and number of particles. So this is where this is so useful in thermodynamics. So there you go, that's moles.